In a today class, we are going to learn the location of the nodes in a finite elements analysis. So this is very important to understand to define the exact location of the nodes. As we know that nodes are formed when it connect with the another elements. Okay, so in finite element analysis, the location of the node is also the another important factor when, for example, if a particular object or the domain that suddenly changes their geometry, or it may change the material properties, or due to the external loading condition, like the nature of loading, it may be temperature, etc., or some different loads nature, right? So for example, if you take an element having an uniform bar for the entire the span, and if you say the one end is fixed here, so for this particular a uniform bar, the cross section area of this element is uniform. Okay, and again the length of this element, it may be L here. Okay, and material properties of this will be E, Young's modulus. So these are the general properties. And loading condition, for example, the load is applied along the axis. Here there is an F. Okay, now for these cases, how we can define the location of the nodes? Okay, so for example, if you take this here, it's an beam, so there is an axis line, center line for the particular beam. Now for in general, if you define here, there is an element 1 and here there will be element, sorry, here there will be node 1 in a line diagram. If you make into the line diagram or discretize form, same object we made into discretized element. Okay, so here for this fixed end, it's an node 1, and for the another end it's free. Here there will be node 2, but you can add for this element because it's an finite element, so you can divide this element into number of parts. So where you can divide, anywhere you can divide, or here you make this L into equal parts, like say L1 and L2, where L1 is equal to L2. Okay, now divide that total length into two parts. Now here at this midpoint, we can say it is the another node, say node 3 will be added here, where node 3 is an optional for you. Okay, again if you want to increase the more number of division, let us divide again this into equal parts like this. So here it will be node 2, node 3, node 4, and finally node 5, like this. Here it will be 2, it will be 3, 4, and 5. So same element we are divided into 4 equal parts. Okay, for this particular case, where the node 2 and node 3, node 4 are the optional. Okay, for the optional. In that purpose, we have divided such cases. Okay, so it is about the axial loaded bar. In case of axial loaded bar, right? So there is another case where we can make, for example, if there is an beam element and it's having some supports at their ends, say some supports, okay, some supports which will be applied here, and it's having an UDL or some different types of loads. It may be acting entire this span, okay, having some quantity. Okay, so the load is applied, and in this case again, if you made this is into uniform discretized element, so here there will be node 1, here there will be node 2. Okay, that's the general method. But in FEM, you have to divide into more number of finite elements. So again, this total length of this beam we made into two parts, okay, at the mid we can say, okay, middle part. So here it becomes now L1, from here L2, so middle part, say the node 3. So here we add node 3. So again, in this case, the node 3 it becomes an optional in this case, because it's a beam of uniformly distributed load throughout the length, and the length is divided into equal parts. Again, in this case, where L1 is equal to L2. Okay, in that case, we have divided. So where 2, the node 3, it is become an optional in this case also. Okay, now we'll see the another case. If you take a bar, again a bar or beam you can say, so here this is an two elements here, say this is an element 1, this is an element 2, and if you fix this end, it becomes an beam. Okay, now the load is applied along the axis, then the force will be applied here. So whenever the load is applied along the axis, it means it's a bar, stepped bar you can say. If the load is applied along the axis, if the load is applied perpendicular to the axis, then it becomes an beam. That is the difference between bar and beam. Okay, so here in this case, it is an axially loaded bar with a different cross sections. Okay, you can see for element 1 there is a large cross section, where for the element 2 there is a small cross section. So what happens here, there is an discontinuity. What happens? Discontinuity in the geometry, right? It happens in the geometry, thus there is a suddenly changes in the geometry here. Okay, from some, for example, if you say this is 50 mm diameter and it suddenly changes to 20 mm diameter. Okay, so there is a changes in the geometry, and the length for this element, it may be L1, this may be L2. So here L1 may or may not. Okay, so may or may not equal, may not be equal to L2. Okay, L1 can be equal or unequal, that is not matter here, but it matters in the geometry because it changes the geometry. In that case, how you can define the nodes? So for entire the bar, draw a discretized element. Okay, so if you say this is the node 1 at fixed end, and from here to here it will be node 2. At this area it will be node 2, and now at the end it will be node 3. So this node 2, it's an mandatory here. It is not the optional, it is an essential here. This node 2 is essentially, we have to take it here, we have to consider it, because there is an suddenly cross section area is changed. In that case we have to consider the node 2. Okay, so similarly in the beam element also, if you are having a beam of uniform cross sections, say uniform cross section, and supports at their ends, and load is applied at the middle. Okay, it may be at the middle. Okay, let us say load is applied at the middle, and here it's an L1 and it is an L2. From here to here, this will be length 1, this will be L2. Okay, so how to make the discretizing this element? Draw a line diagram. Okay, so here at the fixed end, it means where there is an supports, so that will be termed as node 1. At the another end it will be termed as, you can say, 2. And at the middle where the load is applied, it's based upon the loading condition. Here there is an point load or concentrated load that's applied somewhere at the beam, on the beam, so that node will be considered. Even the if load is here is applied some one more load, so there the node will be considered. Okay, like that. So based upon the loading condition, the nodes will be taken. Okay, this is another case. And if there is an for example, there is an another case when there is a beam, okay, and the different loads are applied. For example, one is uh, same we'll say UDL, which is applied for the total length of the beam, and the supports will be at their ends. So in this case, the beam of distributed load having different values. For example, this is the one value and this is another value. So both are having different values, even though they are UDL, uniformly distributed load, but having different loads. So it's an discontinuity. What do we say? Discontinuity in loading. Okay, as like discontinuity in geometry we have learned, same thing, discontinuity in loading also, because the loads are changed here. It means from here to here there is an element 1, and from here to here it's an element 2. Means the loading nodes are from here to here. If we made this as in the line diagram, so here it will be node 1, here it will be node 2, node 3, and this is element 1, this is element 2. So this 2 is an essential here, because there is a discontinuity in loading condition. This is another case. Now we'll see one more case when we are having the composites material, like changes in the material properties or discontinuity in the material properties. Such example also we are having. For example, here we are having one fixed end and having a bar. Okay, but this is an uniform bar with different material. So from here the half of the material is aluminum, if you take, and from the another half is an steel, let us say steel 2, different metals are joined together or combined together, so it becomes an bimetallic bar. Okay, bimetallic bar. So for this case, again it's same as here. It will be node 1, node 2, node 3. Elements are 1, 2, and nodes are 1, 2, 3, where the materials changes. Okay, in that case also we can see. So in this type of different examples I try to explain. So hope you understand, and thank you for your supports. Keep watching my videos and keep supporting. Do subscribe. Have a good day.